Hi, so my name is Clark Lopez and welcome to my lecture where we will be discussing about climate change. Particularly, we will try to discuss why climate change is such a big issue in the 21st century. 20th century, right? Um, we will try to look at why policymakers are looking at this problem right now and, why climate change is such a big deal right now. So let's start. All right. So climate change is the problem where the average global climate is changing in an unprecedented way, which was not seen before. Because of human activity. Now, climate change is a problem because if we increase the heat, we don't know if we can adapt to the our environment or even the other organisms that live in Earth. So, but before we discuss that, let's first discuss Earth. Now, Earth is the planet where we all live in, right? So, it is the planet where life can thrive, and in our solar system, we can see any planet outside there where life thrives, or we don't know yet if there are life on other planets, but Earth, as we know it, this is the place where we call home, where we grew up in, and where human civilization exists. So yeah, Earth. So our Earth is located at the middle of the solar system. Now, the climate that we experience here is not too cold or not too hot, or this is what we are in the Goldilocks zone, where as the story goes, it's not too cold or not too hot. Now, if you look at this picture we have right now, if you can see planet Earth, here it is, right? So we can see that planet Earth is really in the middle. Now, here's the Goldilocks principle that we are saying earlier, where we said that it's not too cold, it's not too hot. It's just right, where we can adapt to this certain kind of environment and where life can adapt and survive. So, just like we said, planet Earth is the place where we can see and identify life living everywhere. For example, this dog, you can see him smiling and he loves his environment. And because we can see that he is adapting to the great climate of the Earth has, and it's the dog has the resources that he needs in planet Earth. So let's go back to planet Earth. Now, over the course of Earth's history, it experienced shifts in climate. The one we are experiencing right now is not new. All right, we always experience shifts in global climate and temperature in the past. So, for example, have you seen the movie Ice Age? Right. So Ice Age is based on the temperature that we experienced in the past, millions of years ago, before even humans existed in the planet Earth. Sorry, this is an exaggeration of the Ice Age. All right. So this is as Ice Age. Now, of course, there are also periods of time where we experience super hot climate, like before any life was observed in planet Earth, or for example, when Earth was newly formed. We call that the opposite of Ice Age as Interglacial Period. Now, Interglacial Period is not exactly like the photo we flash in the screen right now. Again, that is just an exaggeration of the climate of that we experienced in the past. Now, the interglacial period is like the opposite of Ice Age, where we experience warm climates. Alright? So, next. Let's go back to Earth. Now, we experienced interglacial periods and ice ages in the past, right? We mean that we experienced hot and cold climates in the past. But over some time, it adapted and created an equilibrium between the temperature, where we have a very nice climate where every life can live in. Alright? So, as time goes on, the super hot and super cold climate equilibrate, alright, to create a new and warm and nice climate. Now, because of that climate, life thrived and humans even existed during that phase. For example, this one. That person, let's call him Arthur. So you can name him all you want. So anything you want, you can name him. Alright? So now Arthur is the first human to ever existed on Earth. Alright? Now, humans are very unique species because, they adapted in a short amount of time. And looking at the history of the Earth, you can see that over millions of years ago, before the Earth was formed. But when humans existed, it was only a fraction of that time relative to the formation of the Earth, where they learned and harnessed the capacity to build and create civilizations, alright? And they created modern advances. Now, during Arthur's time, it was that time where we learned to first catch animals as food or as clothing, right? It was that time where we first learned how to harness the gifts of nature, right? Here, it was after that time we thought that we can just rely on hunting and gathering resources. So we learned to plant, we learned to farm, right? We learned to cultivate land where we can easily accumulate food as our resources. So as time goes on, humans' civilizations capacity to build materials and innovative ideas where every time they make their lives easier. Okay? So next, we can see here they learned how to create shelter, and they learned how to use fire as a means to cook their food. Alright, next. Now, as time goes on, as I said, human civilizations learned how to cultivate everything that's around them and use it in an innovative way. And I find it interesting that humans are really, they are really amazing because they learned how to create something useful. And it's amazing to think that starting from this civilization, we are here right now and we are talking face to face. I mean, online. So after some time of after some time of development, learning, we landed on this era. Now, this era is what we call the Industrial Revolution. This is the time where we created machines centered on steam engines. This is the time where we use energy sources that come from land. This is the time where we learn how to create new transportation, like this train, where we use steam engines as a means to its engine. During this time, we created new amazing things like the first car, which is also powered by steam engines. The pistons and the mechanisms of the engines that we are using then and even now are based on the scientific concept of steam engines. Now, that's really interesting. So, let's go back to this image. We can see here that even though we humans have come a long way and we have invented new things and many things that can help ourselves to improve our civilization, there are still consequences that needs to be sacrificed in order to harness these technologies for ourselves. As you can see here in the photo that we have, emissions, we can see that smoke, right? Those smokes are what we call carbon dioxide. And during that time, we released many amounts of carbon dioxide into the atmosphere. Now, here is what we know right now. Because of humans' improvement and creation of new technologies, we created byproducts that are harmful to the environment. For example, the carbon dioxide emissions that we emit during factory works. Now, those carbon dioxides, as we will talk about later, help contribute to warming up our planet. Now, even though we said earlier that the Earth is experienced climate change in the past and even high temperatures in the past, those were natural occurrences, while this one that we are experiencing right now is man-made. Alright? Now, man-made, and we will talk about that later. Now, you can see here in this image that the globe is warming up. And that is what we are experiencing right now, and that is this Earth. Alright? Keep this in mind. Keep this picture in your mind, because I think it is important to know where we are heading if we don't change the actions that we are doing right now. Alright. Now, maybe there are some doubts out there. Like, many people are asking or doubting the science of climate change. Because, we don't even feel it. We don't even see it in our environment. We don't even experience the heat that is building up in our globe. Even though the science says that the Earth is heating up. Get what I mean? We sometimes don't believe the science because we don't see it happening actual. I watched this movie called Don't Look Up. It's a great movie, by the way. Don't Look Up is a science movie where the Earth was going to be struck by an asteroid, but the people didn't believe it because the asteroid can't be seen from the sky, right? Now, not until they saw it, that the asteroid were really coming. But when they learned that the asteroid really was going to hit the Earth, it was too late, and they can't do anything in order to destroy the asteroid and protect planet Earth. So, we all have this belief that to see is to believe, right? We wouldn't believe something. We wouldn't believe something if we don't see it first happening in our environment. So, now, I hope that this lecture will remove that doubt. We remove the doubt against the science of climate change, because climate change is really really real. climate change is real, even though we don't see it and experience it. I mean, we experience it, but we don't. It's not like what we expect to happen. You know. So, the first doubt that we all have is, how serious really is climate change? Now, most of us think that climate change is not serious. You know, there are people out there who thinks that climate change was what's a conspiracy theory, where there are a lot of interesting topics out there with regards to the science of climate change. Now, the point I'm trying to make here is that many people don't believe that climate change is really serious. Next. Now, there are also beliefs that humans can't cause climate change because the Earth is huge. I mean, how could us humans even affect the climate of an entity so big? You know, how can we affect the globe? I mean, it's huge compared to humans. Now, there are those out there, people out there who think like that. You know, they don't believe that we humans cause climate change, and it's only natural to experience that, to experience the CO2 emissions. I mean, it's only natural to see the CO2 emissions that we have in our atmosphere right now. Okay, the third doubt that we all have is, I mean, this is not a doubt, but there are a lot of people out there who know about this topic, who are knowledgeable about the topic of climate change, but they refuse to act because they don't know what to do. Alright? They think that they are only a single individual who can do anything, and it's up to the policymakers and big company, the tech giants, to solve this problem. But I think that's not true. Even a mere individual can help solve the problem of climate change. I mean, everyone can help in solving this problem, as we will talk about that later. Now, this is me. Now, at first, climate change, I thought that climate change at first was, you know, I was like the people who doubt the science of climate change before I researched about this topic. You know, when I was in grade 9 or grade 10, I thought that climate change was a problem, but I didn't really understand why it was a problem. I only knew that climate change is a problem because my teacher asked me to research about that topic and wrote something in my notebook. And I didn't really understand the science of it. So, during that time, what I thought about climate change is this. Climate change is a change in climate. Funny, right? Okay, so here's what I'm trying to make here. Point being is that I'm only an individual who learned a lesson with regards to climate change, and I wish to share that knowledge with you. This lecture is for any individual out there, even a teenager who needs something to write in an assignment like me, even parents and even professionals, I hope that you know, we can have a discussion out there in the comment section below. Now, the point being is that this lecture is for anyone, and I hope that I explained myself clear. Alright? And even though if I didn't explain everything clear, I hope that you will believe that climate change is real. believe the science, and if you don't understand anything from this lecture, blame it on me. All right. So let's start. First, before discussing climate change, I want to make a hard line or distinction between climate and weather. Now, as you can see in the picture right now, we are referring to climate in the globe, where we can see temperature changes, and weather as the picture on the right. Now, let's first discuss climate. Excuse me. Now, climate is a variation in the average temperature in a long period of time. Climate is what we expect to see happening in our environment. For example, during, if the month is December, we expect to feel that the climate is cold, because December is the time where the Earth is far from the sun in its orbit. That is climate. That is the weather, or that is the temperature that we expect to feel. All right, with regards to the natural variations. For example, the distance of the Earth from the sun. That is what we expect to see or to happen. Now, climate can be described by variations in the climatic system. Mainly, these are the atmosphere and the other spheres, like the hydrosphere, lithosphere, and so on and so forth. Now, climate can be described by the interaction of these spheres, as we call it, right? So, climate changes as the factors, or the components of these spheres varies, right? So, next. Now, since we have a basis to understanding how climate may change, we can say that it is predictable, right? But how predictable is climate? Now, because we can monitor the spheres, as we call it, we can calculate what will be the change in the climate in the Earth in the long run. All right, so it is predictable. We can compute for the values of temperature changes that it can induce on Earth. So next, we will talk about weather. Now, weather is what we see from day to day. For example, you see that the weather outside is cloudy, right? That is weather. But when we say climate is the long-term variation. For example, imagine the stock market. As time goes on, as the economy builds, the stock market in the long run will rise up. But if you are looking at the short-term basis, you can see tiny fluctuations in the rise of the stock market, right? Now, that long-term rise of the climate is what we expect to see or to happen. So we can refer to that as the climate, while weather is the tiny fluctuations in the long run. All right? So weather is fluctuations in the atmosphere, and so weather is only a day-to-day variations in the atmosphere. We can always see it changing, the weather. We can always see the weather changing. For example, if we see that it's sunny outside, maybe tomorrow we will see that it's cloudy. Now, weather is very difficult to predict, because we can predict it, and there are variations in there are many factors in the there are many factors that can affect weather. For example, the mountains, the geographical geographical arrangement of lands. All right. So therefore, it is affected by a lot of factors. Now, because of this, because weather is affected by a lot of factors, it is chaotic, meaning we can predict it, just like we said. Now, here's what's interesting. Climate and weather have a relationship. Now, we can know, somehow we can identify the weather if we know the climate. Alright? So there is like a relation between the two. For example, if the climate in December is cold. Now, if the climate is cold, we can somehow have an idea with regards to the weather that it will not be sunny, right? Or most of the weather will be rain and downpour. So somehow there is certain relation between weather and climate. Now let's go back to this picture. Now, before we tackle climate change, there are three factors. There are three factors which I think is important before we tackle in order to understand climate change better. We have to understand three factors first. Now, I want to talk about the carbon cycle. All right, we are talking about the carbon cycle in here. So yeah. So when the Earth, when the planets first formed, we all know that. I mean, some of us. We have an idea that the creation of the planets is from the explosion of stars, right? And as the star explode, which are composed of hydrogen and helium, as this star exploded, new elements were formed. All right. So there, from the reaction of hydrogen and helium that are the composition of the stars. Now, because of that explosion, the other elements were created. For example, the first elements that were created or present were hydrogen, as we all know, because it's from the star, and helium. But after some time, as the star exploded, there are reactions which formed the new elements. Now, these first elements were oxygen, carbon, nitrogen, and argon. Alright? Now, these are gases which are very lightweight. I mean, they are very light. So, they are the first elements that were present in the universe. Next, after some time, the heavy elements or metallic elements were formed. These were iron and silicon and the likes of them. Alright? So, next. The planets were formed due to the collision or the aggregation of dust particles and rocks out there. Now, as you can see here in the image, this is how we can view the Earth in its early infancy times. Now, the Earth, at first, it didn't have an atmosphere. Alright? The Earth didn't have an atmosphere. It only took a beating from the rocks that were thrown at it. But, after some time of formation of the Earth, we entered the period of the Hadiyan Period, named after the god of death or god of the underworld, I think so. And which is the god of the underworld, named Hades. Right? We entered that period. Now, this is the period where the atmosphere was formed. How? Okay, so there are cracks and there are volcanoes during this time. Cracks in the crust of the earth. Now, the mantle of the earth contains carbon, hydrogen, and carbon dioxide. Carbon dioxide, water vapor compounds. Now, this since the mantle is very hot, these gases will then slip through the cracks in the mantle and through the volcanic activity. Now, during this time, carbon dioxide and water vapor were emitted into the atmosphere at a long period. So that is when the first atmosphere was formed. All right. Now, since carbon dioxide is the concentration of carbon dioxide is very high during those times, we can say that the global temperature at that time is very hot. Okay? So, next. Now, maybe you're asking, how did the Earth, from this period to now, how did that temperature change and the global concentration of carbon dioxide decrease? Alright, how did that happen? So, that is because of the carbon cycle. Now, the carbon cycle plays a very important role in the understanding of climate change. First, the carbon cycle in the atmosphere then sank. Over some time, let's go back to the Hadiyan Period, alright? Now, over some time, the Hadiyan Period entered a new phase where water or oceans were formed. Now, the atmospheric concentration of CO2 was decreased due to the carbon cycle, where carbon dioxide in the atmosphere reacts with the newly formed oceans in order to form carbonic acid, or that is soda. We all do not know that, right? So the reaction goes like this. Right, that's the chemical equation of the carbonic acid. Now, this carbonic acid, the carbon dioxide in the atmosphere, right, reacts with the ocean to form carbonic acid, which means that there must be a decrease in the atmosphere. So, next. Now, since the carbonic acid contains hydrogen and carbon and carbonates compound, it will react, carbonic acid in the ocean. After their reaction, carbonic acid then reacts with the ocean floor and the rocks. Alright? Now, how does that look like? Now, carbonic acid reacts with metallic elements or metallic elements, for example, magnesium, calcium, in order to form what we call carbonates. Now, these carbonates are very dense, right? They are very dense and they sink to the bottom of the ocean. Therefore, they're moving the carbon dioxide, in the atmosphere. Alright? Since the newly formed carbonates sink into the bottom of the ocean. But that is not enough to explain the carbon cycle or the carbon reduction during the Hadiyan period. Now, the carbonates on the ocean floor, we all know that tectonic plates have a tendency to move. Now, these carbonates in the ocean floor are then stuck under the crust of the earth into the mantle. Alright? Now, when these carbonates are in the mantle, the forces that binds the constituent elements in the carbonates are then separated or isolated from each other because of the heat that they experience in the mantle. All right, so they are reduced to their constituent elements. Therefore, magnesium, carbon, and oxygen. Now, carbon is then placed in the mantle. All right, but over some time, the carbon that is stuck under the crust or in the mantle is then re-emitted back into the atmosphere. How? That is through volcanic activity, right? So as time goes on, volcanoes will erupt and then re-emit carbon into the atmosphere. Now, over some time, the carbon concentration in the atmosphere would be reduced because there will be an equilibrium between the two. Now, this is how we can view that, right? As we can see from this image, we can see that the concentration in the atmosphere is 600 GT or gigatons. That is millions of tons. So as we can see from here, that as we can see from this image, there is an equilibrium because the atmosphere emits its carbon dioxide into the ocean, which then sinks under the crust or into the mantle, which is then re-emitted through volcanic activity. Now, when we humans entered the scene, this equilibrium was destabilized. Alright? I mean, there is only a certain amount of oxygen that is released naturally. Now, what if we humans added or contributed to this carbon cycle? What do you think will happen? Well, of course, the carbon stored in the atmosphere would increase, therefore also affecting some of the components that is involved in the carbon cycle equilibrium. So this is what's happening right now when we add CO2 emissions into our atmosphere. We increase the carbon concentration in the atmosphere, which we destabilize the equilibrium that nature created. So maybe you're thinking, what does this carbon emission into the atmosphere have to do with us? Maybe it's just nature. Well, maybe you're thinking like that, but as we said earlier, humans are during the time of the Industrial Revolution, we increased CO2 emissions. And if you don't believe that the equilibrium is destabilized, we always monitored the CO2 concentration in the atmosphere, and one of which is through the use of the killing curve. I find it interesting that the name is the killing curve. So here is the killing curve. Now, it was started in the 1960 by a man named Killing. I forgot his first name because I'm nervous right now. So, as we can see, during 1960, the increase in CO2 concentration in the atmosphere is going up till now. Right? Now, I want you to note that the red fluctuations in the CO2 concentration is due to the respiration of the earth, like spring and winter. So, maybe you're asking, well, this data isn't enough to support that humans increase the CO2 concentration in the atmosphere. Well, that's true. But what if we look at the past and extended the graph? As you can see from this, the increase in the slope in increase of the CO2 emissions, I mean CO2 concentration in the atmosphere is very high. So what? Maybe someone is asking out there. Well, if we extend it even further, we can see that the spike in the CO2 concentration in the atmosphere is very, I think it's very amazing and very incredible that the CO2 concentration has reached that high. Now, maybe someone's thinking, well, since the Earth has changed its temperature or climate in the past, then this data only shows thousands of years ago. So, how do we know that nature isn't just doing what it experienced in the past? Or, I mean, how do we compare this data into the data or the experience that the Earth experienced in the past? Alright? Do you get what I mean? So, in order to see that this was not just this is not nature's doing, we have to extend the graph into millions of years ago. Alright? And we do that through the use of climate proxies or clues that are hidden in the Earth or ice cores, as we will discuss that later on. Now, if we extended this graph into millions of years ago, we can see that the spike on the current time range or range of time is very unusual, because thousands of years ago, not millions of years ago, thousands of years ago, we can see that the global average of CO2 emission never reached or never got past 300 parts per minute. 300 parts per million. Alright? It was then only during the time range that we are in right now that we reach 400 parts per million of CO2 concentration in the atmosphere. This is very, when I saw this graph, I thought it was really amazing. Even though we humans are the cause of it, I mean, it's really amazing. And this is the data that showed me that climate change is really a big deal. Now, how did we manage to change the global concentration in the atmosphere? Well, or do we even have the power to change the global concentration of the Earth? I mean, the Earth is very large, right? How can us humans change the CO2 concentration in its atmosphere? Well, when we look at the equilibrium earlier on the image of the equilibrium or the box model of the equilibrium in the carbon cycle, we can see that the ocean and the Earth have a stored carbon in them. All right. Now, just like we said earlier, humans are very amazing creatures, and then over time, we humans learned to create new energy, or to find energy sources. Now, during the advancement of science, we learned that the Earth and the ocean have a stored carbon in them. Now, it was only sometime during the during the modern era where we learned to harness this stored carbon and use as a fuel or energy source. As you can see from this graph, 6,000 gigatons of carbon is stored in land, alright? And then 38,000 gigatons of carbon is stored in the oceans. Now, if we just pause and stop and think about where do we get our energy sources? Well, we get our energy sources from coal or even from plants, right? I mean, we use that as fuel. And still, if we still think, where do we get the gasoline that we use as an engine for our cars and for cooking? Well, right, we use oil. But where do we get petroleum and oil? Now, oil is hidden in the land or even the ocean, right? That's why there are oil companies looking at the ocean as a source of oil. All right, so we know that humans had the capacity to change the atmosphere because we learned to harness the stored energy in the oceans and the land or the earth at a short amount of time, and we harnessed it and used it at a long period. All right, we learned to use it as our energy source, and it is the foundation of the modern era. Now, how do we know, or what does carbon dioxide in the atmosphere even have to do with the increase in global temperature? I mean, do carbon dioxide and temperature have a relationship? Alright, now, keep that in mind. Now, a scientist named Jean-Baptiste Joseph Fourier, or we can just call him Joseph Fourier. Now, as we all know he is a famous mathematician who created the Fourier analysis. Now, Joseph Fourier was also a very he likes to ask questions, right? Like all scientists, they all like to know what they see on their surrounding. They like to understand what is happening. Now, after some time of wondering and asking, he stumbled upon the question of how are we experiencing the climate or the global temperature that we are experiencing right now. Now, Joseph Fourier asked himself, how does the phenomena where we experience a very wonderful climate where we can live in. Now, Joseph Fourier knew that there was something that traps the sun. I mean the radiation that comes from the sun, and he also provided the a mathematical expression or a mathematical explanation to this phenomena. Right? So here is what he said. Now, as you can see from this image, we have two circles. We will say that the orange or yellow circle is the sun and the blue circle is the earth. But Joseph Fourier said, if the sun were to emit its radiation back to earth, the earth will accept it, alright? The earth will accept the radiation that comes from the sun. But what Joseph Fourier said, the earth will then heat up and then re-emit the radiation that comes from the sun as thermal radiation. Alright? So as a note, the radiation that comes from the sun is at the visible light, and the radiation that the earth emits is thermal radiation. So going back, as Joseph Fourier said or implied in this scenario, the power that the sun directed towards the earth is equal to the emission of the earth. Now here's the equation. P refers to power and E refers to emission. Alright? This is what Joseph Fourier said. He said that everything if the sun were to radiate its heat towards Earth must be re-emitting that radiation out into space. And therefore, we should experience a world like this. He said that if that was true, then we should see that the earth is like this, a cold, barren place where no life can thrive. But Joseph Fourier said that that is not what we observe. So there must be something that traps the heat or traps the emission of the earth and re-emits that back into earth in order to warm it up or warm up the lithosphere. So what Joseph Fourier said, that the emission that comes from the sun is then accepted by the earth, but there must be something that traps the re-emission of the earth out into space. There must be something, there must be some entity that traps the heat from escaping. Alright? The re-emitted thermal radiation by the earth is fractioned. Alright? As you can see from here, if the power, if we experience a warm climate in earth, then there must be something that prevents the re-emission of the thermal radiation out into space. Alright? Now, as you can see from this equation, we can see that the emission of the earth is fractioned. But, as you can see, the amount of the solar radiation that comes from the amount of radiation that comes from the sun is greater compared to the re-emitted radiation by the earth. So this means that the radiation that comes from the sun is much greater than the amount of radiation that leaves. Alright? So if this were true, then the earth would continue to heat up. Alright? Because the energy or the radiation that comes in is less than the radiation that comes out. So therefore, the earth must heat up. So how is it that the earth is not heating up? Well, it turns out that if the earth has a protective layer, or the entity that absorbs the radiation or prevents the radiation from exiting the earth, then we must focus on this entity. We must focus on the atmosphere, or this entity that prevents the radiation from leaving Earth. Alright? In order to see what is truly happening. Now, let's we will define, we will say that the atmosphere is the variable A. Alright? And then we will define A, or the atmosphere, as the absorbed radiation. Alright? Because the atmosphere absorbs the radiation that is supposed to come out of Earth. Now, A is equal to Earth, emission of the Earth times the fraction that is absorbed. B refers to the fraction that is absorbed by the atmosphere. The radiation that is absorbed by the atmosphere. Now, if the atmosphere were to re-emit its radiation back to Earth, in order to keep the warm climate, then it must be that the emission of the atmosphere back to Earth is half the emission. Half the emission that is supposed to come out of Earth, or it is half the amount. It is half of the amount that It is half of the amount of the temperature or the radiation that the atmosphere has. So, a fraction of the heat content of the atmosphere is then re-emitted back into Earth. But then, if this were true, the atmosphere will continue to heat up because the atmosphere is supposed to be the amount of heat that comes in must equal the amount that goes out. All right. Now, as you can see here, the amount of the radiation of the amount of the radiated emission back. The amount of the radiated radiation in the atmosphere is half. Now, if this were true, then the atmosphere will continue to heat up. So there must be something that there must be a scenario where the atmosphere re-emits another fraction of its radiation out into space, in order for it to not heat up. So, in order for the atmosphere to be in equilibrium or not change its temperature, the amount of the emission must equal the amount that comes in. Okay? So, here. Now, as we can see here, the amount of the emitted radiation is less. But if we took into account the amount of radiation that the atmosphere gives, we can see that the equation will equal. All right, the amount of radiation coming in will equal the amount of radiation coming out. So, in order for the Earth to be in equilibrium or not change its temperature, the amount of radiation that comes from the sun must equal the amount of radiation that the Earth emits plus the amount of radiation that the atmosphere emits. Alright? Next, in order for the atmosphere to be constant or not change, the temperature of the atmosphere to not change, the amount of radiation that it absorbs must equal the amount of emission. Right? The amount of radiation that absorbs must equal the amount of emission in both directions, back to Earth and out to space. Alright? Or else the atmosphere will heat up. So, what is important to know here is that the energy that comes in must equal the energy that comes out, or the radiation that comes in must equal the radiation that comes out, in order for the atmosphere or the Earth to not heat up. Now, if we were to take into account the emission of the Earth, the fraction of the emission of the Earth out into space if we took into account the surface shape of the Earth, we will get this equation. You know, the surface area of the a sphere is 4 pi r squared. So times the K, a constant, which we will not talk about, and times multiplied by the temperature. Now, as you can see from this equation, we took into account the surface shape of the Earth. Now, if we were to look at all of the equation, we can see that the absorption rate is present in all of the equations. Alright? If we were to look at all of them, we will see that the amount of emission, the amount of the absorbed radiation affects all of the equations. So, which means, if this absorption were to change, guess what will happen? Everything will be affected. If this absorption rate were to change, everything will be affected and change, therefore not stabilizing it, and it will affect the equilibrium. Now, if it affected the equilibrium, something must change. Alright? If we look at this equation, we need to know what will change, or we need to know what will change value in order to equilibrate the equation. And it turns out that the temperature will need to change if the absorption rate were to change. Alright? The temperature will change if the absorption rate were to change in order to equilibrate the equation. For example, let's say that the amount of solar energy that the sun gives is 100, and then the amount of radiation that the Earth emits is 100 multiplied by the fraction that is absorbed, which is the absorbed emission is 0.45%. 45% of the total emission. 55% of the total emission. Alright? So, as you can see from this, the absorbed radiation that the Earth emits, or supposed to emit out into space, is 100, the total emission of the Earth multiplied by the 45%. Okay? So, as you can see from this, if this were true, then everything is in equilibrium. Alright? Everything is in equilibrium. Now, since everything is in equilibrium, we need to calculate the temperature. By the way, we simplified the surface area, or the emission of the Earth, and only took into account the temperature, as I think that this will be much easier to understand. So, in order to identify the temperature, we need to manipulate the equations that we have. Alright? And it turns out that if the emission that comes from the sun into Earth was 100, and the emission, the absorption is 0.45%, 45% of the total emission that is supposed to leave Earth, then the temperature must be 100. Okay? Now, keep this in mind. So, next. As we said, if the absorption rate were to change, for example, we change the 0.45 to 0.55, we can see here that the amount, or if we calculate, or if we solve this, the amount of emission that leaves Earth is less than the amount of the solar energy that comes in from the sun. Meaning, the Earth will continue to heat up. Alright? Or, it will continue to heat up if there was nothing to if there was nothing present in order to equilibrate it. Now, if this were true, we can see an inequilibrium or a destabilization of the energy that comes in and energy that comes out equilibrium, which we supposed to see. Now, since we said that as you can see here, that the amount of radiation that the atmosphere emits is remained the same, because the emission of the atmosphere remains constant and it never changes. All right, the amount of the amount of emission that the atmosphere emits into space never changes and it remains the same. So it cannot account for the change or the inequilibrium. And it turns out that if this were true, we need, as we said earlier, temperature will change depending on the absorption rate change. Now, if we calculate for T, given the absorption rate that we have right now, we can see that the temperature increased by 22 by 22 units. All right, just like we said earlier, if the absorption rate were to change, the temperature of the Earth will change in order to account to the destabilization of the equilibrium. All right, the temperature temperature must increase or decrease in order to account for the change in the absorption rate. Okay, so during the time Jean Fourier. All right, now we only know that there was something that traps the heat. All right, by the way, this time was when the greenhouse effect was born. All right, this is when the greenhouse effect word was first used. So again, during this time, we don't know what was trapping the heat in the atmosphere. We only know that there was something that must be trapping the heat. Okay, then it took another scientist in order to explain this phenomena. Meet this guy. Now, this guy is John Tindall. Now, during that John Tyndall's time, he was aware of Jean Fourier's endeavors with regards to climate. Now, he tried to unravel the story, or he tried to know or identify what was trapping the heat in the atmosphere. So, what he did was he wondered what was trapping the heat, or what was preventing the heat from coming out of the sun. Out into space. So then, what John Tyndall tried to do was that he conducted experiments with the gases present in the atmosphere. All right, because that was reasonable. He conducted experiments with regards to the absorption rates of heat absorption of the gases present in the atmosphere. He conducted experiment as to what kind or how much heat can the gases present in the atmosphere absorb. All right. Now, the atmosphere is built up of many compounds. Many compounds and elements. Now, during John Tyndall's time, 78% of the elements present in the atmosphere was nitrogen. Then, it was also 20% oxygen and 0.9% argon present in the atmosphere. And 0.03% of carbon dioxide was only present during that time. Now, remember that this data was during the time of John Tindall, and the amount of concentration in the atmosphere of elements and compounds that we have right now is different than it was before. Alright? So, what then John Tindall did was that he experimented on the absorption rate and what kind of radiation do these gases absorb. What John Tindall found out was that each gases present in the atmosphere have their own fingerprints, or they have their own range of wavelengths of radiation which they can absorb. Alright? They have certain types of radiation or fingerprints of radiation which they can absorb. Now, what John Tindall found was that the carbon dioxide and water vapor present in the atmosphere have the capacity to absorb radiation, which was in the wavelength of thermal radiation. Okay. Now, since the thermal radiation is supposed to live into space, right? Just like we said earlier, thermal radiation is the type of radiation that the Earth emits. Then, carbon dioxide and water vapor must play a role in the prevention of the thermal radiation from escaping Earth. Okay? So, John Tindall said was that carbon dioxide and water vapor have the capacity to store heat and prevent it from leaving. Now, what then John Tindall concluded was that carbon dioxide was not the main cause of the climate that we are experiencing right now. Rather, it was due to water vapor, which absorbs much more radiation compared to carbon dioxide. Which was true because water vapor really absorbs heat better compared to carbon dioxide. But then, another scientist entered the scenario. Enter Svante August Arrhenius. Now, we can also call him Svante Arrhenius. Now, what Svante Arrhenius found out was that CO2 emissions can really increase temperature by what he found out was that as we increase the CO2 concentration in the atmosphere, we are increasing the range of radiation that the atmosphere can absorb. Or it goes like this: the CO2 emission, the CO2 concentration in the atmosphere accounts for the we said earlier that we have that the gases present in the atmosphere have their own fingerprint, right? Or the range of wavelength of radiation that they can absorb. What Svante Arrhenius found out was that the fingerprint of carbon dioxide, when combined with the fingerprint of hydrogen, water vapor, if those two were combined, the range of the wavelength of radiation that they can absorb will increase. Meaning, carbon dioxide doesn't have a larger capacity to store heat, but it can increase the range of wavelength of radiation that it can absorb. Alright? Now, what Arrhenius found out was that as we increase the carbon dioxide concentration in the atmosphere by a factor of 3 hubs, we will increase the global temperature by 3 degrees Celsius. Meaning, as we increase the global concentration of the the global concentration of carbon dioxide in the atmosphere in a geometric progression, the global average of temperature will increase linearly, or something like that. Okay, as we increase the global concentration in the atmosphere by a factor of 3/2, the temperature will increase by 3 degrees Celsius. And that is when we know that carbon dioxide can really affect temperature. Now, I want you to look at this. Since the start of the Industrial Revolution, which was somewhere between 1700s and 1800s, and as we can see, the global emission of the carbon dioxide into the atmosphere has been increasing. Okay, it has always been increasing. The amount that we emit up there into the atmosphere has a very large concentration now, right? Because everything that we live up there doesn't live. It's everything that we place up there stays up there. All right. So here this fact using this fact I realized why we are encouraged to plant more trees in order to lessen the carbon dioxide concentration in the atmosphere. I thought that we are encouraged to plant more trees because the oxygen concentration was depleting, but that was not really the case. We are encouraged to plant more trees in order to lessen the carbon dioxide concentration in the atmosphere. So yeah, I just shared that. Now, keeping this data in mind, if we look at the shifts in the global temperature, we can see that the temperature increased. All right, we can see that the temperature went past average since the 1970s and 1960s. All right, and that is because of the carbon dioxide emission that we put up there. Or is it really the cause? If we put these two data side by side, we can see that there is somehow a pattern, or there is a relation into the rise and fall in the patterns of changes in the graph. All right, there is this certain relation in the change in the surface temperature and the carbon dioxide emission. I mean, there's like a pattern. All right. Now keep this in mind because we will get back to this later on. Now, as we said earlier, we have always been increasing the global CO2 emission. Now, because of this, the Earth has been heating up, and we observed that. Now, if we look at the average heat energy in the the heat in the ocean, we can see that it has increased. All right, it has increased. Now, keep in mind that the ocean is a very large. It's very large. The ocean is very large. Therefore, it is very hard to increase its temperature. It will take a long time. However, there is still some fraction of the energy that comes from the radiation that must be stored in the oceans. All right, and this data tells us that, all right, the energy that the ocean contains has increased since the year 1990s, or the modern era, where we increase CO2 emissions. Now, if we were truly to look at the increase in the if we were to look at the oceans as a means to identify an increase in temperature, then we should look at its surface, or the surface of the oceans. As you can see from this data, we can see that the that the surface temperature of the oceans has increased by 1 degree Fahrenheit. Now, maybe you're thinking 1 degree Fahrenheit is very small. Well, yes, that's true, because but you have to take into account that, I mean, the ocean is very large, and there is high water has a high absorption. I mean, water has the property to absorb heat longer. Do you get what I mean? It has the property to absorb heat. I mean, it has the property to reject heat before it heats up itself. All right? I mean, yeah, just like that. We have to take into account the size and the property of the ocean or the surface, or I mean the ocean. Next. Now, remember this. Since we look at this, if we look at this data, we can somehow, again, we said that if we look at this data, there is somehow a relation in the shift in temperature and the shift in the annual CO2 emission that we do. We can see that there is somehow a relation between the two. Alright? But then, how can we be sure that humans are really, the CO2 emissions of humans are really the cause of this shift in temperature? How can we be sure? We can't just compare this data that we have on the annual CO2 emissions of humans to the global shift in temperature, because that is wrong. We are only comparing one variable that can affect the global temperature. We have to compare all of the variables that can change the global temperature in order to prove that CO2, the annual CO2 of humans, annual CO2 emissions of humans are really the cause of the shift in global temperature. So what do we do? So this problem is what we call the attribution problem, because we can just compare the data that we got on the annual CO2 emissions of humans, and given the fact that CO2 can absorb heat and it prevents heat from escaping. Now, given this fact, even though we have a reason to believe that CO2 emissions of humans are the cause of this shift in global climate, we can't do it because science needs to be, in order to test our hypothesis, we need to use all of the variables that we have, or all of the variables present that can affect global temperature. We can just use one variable and be sure to state that humans are the cause of global temperature shift, climate change. That's not correct. Now, in order to solve this problem, of course, in order to test our hypothesis, alright, we need to conduct experimentations. We need to use all of the variables that can affect global temperature and compare them to the actual change in temperature that we can observe now. Now, how do we do this? How do we solve the attribution problem through experimentation? The variables that are present in the atmosphere that can affect global climate is very large in scale. All right, we can just change it in a short amount of time. Years would be the maximum. So how do we do this? How do we compare all of the variables that can affect temperature and prove that CO2 emissions of humans are the cause of the global climatic shift? Well, what we have here to the earlier, since the beginning of this lecture, what we have in order to identify climate change and in order to prove that the CO2 emissions and global temperature changes that we have right now is unprecedented and unnatural. what we have right now are data. Alright? That's what we have right now. Data that we gathered from climate proxies, right? Like ice cores, the ocean floor, everything data. We can use that. We can use that in order to prove that humans are really the cause of the global climatic shift. But the problem with data is that we need to identify the capacity of each of these variables. The capacity of each of these variables to affect the global climatic shift, given the amount that they have in their present with their respective times. So, since we have data, we can use all of this data in order to create numerical models. Alright? Now, numerical models are the weapon that we have in order to attack the problem, the attribution problem. Numerical models are our solution with regards to the attribution problem, and in order to prove that humans are really the cause of climate change. Now, how do we do this? Now, we said earlier that CO2 emissions, CO2, carbon dioxide, and other greenhouse gases have the capacity to store heat, and it can affect temperature. Now, if we relate the amount of the carbon dioxide present at a certain time and the average shift in temperature that it induced, we can use that data in order to model the average shift in temperature that it can do over the long time. Right? It goes like this. If we know that CO2 can absorb heat, and we know the amount that it has, the amount of CO2 present in the atmosphere at a certain time, if we just relate the amount of the CO2 present at that certain time and the amount of heat, temperature shift that it can induce to the global climate, then we can create a model, right? We can predict how much it changed the global temperature. All right. Now, that concept is what we call the radiative forcing. Now, just like we said earlier, if the global concentration or the absorption of the atmosphere were to increase, that would create a destabilization in the equilibrium. Now, that destabilization is radiative forcing. Radiative forcing is just the destabilization of the equilibrium. Now, as you can see from this image, if the absorption rate were to increase and the amount of the absorption rate were to increase, right? The absorption rate of the atmosphere were to increase, we can see that the emission or the thermal radiation that is supposed to leave Earth is decreased. But then over time, the temperature will increase. The surface temperature of the Earth will increase, and over time it will create a new equilibrium. But during that time, the Earth has increased its temperature as a response to the increase or decrease in the absorption rate of the atmosphere. Now, radiative forcing is the tool that we can use as our numerical model. Okay? So, we know that we can calculate for the amount of radiative forcing or the destabilization in the global temperature that CO2 can induce. Now, what if we were to truly prove that CO2 emissions of humans are the cause of climate change? We have to compare all of the variables and calculate their respective radiative forcings. Alright? Now, we need to calculate the variables, the natural variables, and also the anthropogenic variables. Now, some of the natural variables that can affect global temperature is the Melancholic cycles. Now the Melancholic cycles is the change in temperature in the Earth as a result of change in the Earth's orientation with respect or with regards to the sun. All right. Now, the Earth can change its eccentricity or the orbit shape. Right? Now, as we all know, the shape of the orbit of the Earth around the sun is an ellipse. But there are times where the shape of the orbit of the sun becomes a circle. All right? And then there are also times where the wobble or the direction of where the axis is pointing to changes. All right? Changes as time goes on. And then there are also times where the angular tilt of the axis of the Earth is shifted, right? It becomes a straight line and then it returns to its normal angle. Now, if we took into account the amount of temperature change that these factors can induce to the global climate, if we took into account their ability to change the global climate, then we can create a numerical model, right, with regards to their ability to change the temperature. For example, so this is the combination of the three Melancholic cycles. If we combine all of them, this is the data of their average temperature. This is the data of the temperature change that they can induce or that they can do to the temperature of the Earth. Now, this data, I just want you to know that the Melancholic cycles was responsible for the ice ages and the warming periods that we experienced in the Earth's history, right? The Melancholic cycles was the cause of the ice ages. Yeah, I just want to share that. Now, just like we said earlier, we have the data to know what was the temperature in the past, right? That is through the use of ice cores. You know, these ice cores have a bubble trapped inside them, and then layer by layer, these bubbles contain the atmospheric concentration that the atmosphere had during that time. Okay, so now using this data from ice cores, I didn't include that ice cores also store ice cores also store an information with regards to the temperature during their respective times. Okay, that is due to the isotopes that are trapped inside them. Now, if we compare this data that we have from ice cores to the Melancholic cycles, right? If we plot them together, the purple line represents the Melancholic cycles, and the green line is the global temperature, observed global temperature. Now, if we compare that, we can see that the Melancholic cycle has an influence to the observed global climate. Somehow we can observe a pattern of change that the Melancholic cycles induce. Now, this is what we are doing. We are comparing our numerical models to the observed global temperature in order to identify if these variables were the cause of the global temperature change that we are experiencing right now. Right? We are comparing numerical models to observed data. Observed data. Okay? Now, as I said earlier, the Melancholic cycle can explain the ice age that we experienced in the past. Okay? Now, there is also an argument that volcanoes can induce the CO2 emission in the atmosphere. But according to various researches, the amount of CO2 emission that volcanoes emit out into the atmosphere is just a small fraction of the CO2 emissions that we humans do. I mean, the emission that the volcanoes can do is by a factor 100 by a degree 100 less, right? Which means humans are really the leading cause of global CO2 emissions. Now, if we took into account this if we took into account the radiative forcings that the CO2 emissions that came from the volcanoes can induce to the global temperature, we can calculate for the numerical models. Alright? Now, another argument why volcanoes can't be the reason of the increase in CO2 emission is because volcanoes is not the cause of climate change, is because volcanoes release aerosols. Aerosols are responsible for decreasing the heat that comes from the sun. Alright? Now, aerosols are they decrease the climatic change, or the amount of energy that comes from the sun. Alright? Now, just like we said earlier, we calculated for the radiative forcing that carbon dioxide can do to the global climate and global temperature. Now, if we do this to all of greenhouse gases, as we can see that carbon dioxide is really the cause, or is the leading cause of temperature change over time. Again, if we look at this data, we can see that the temperature has increased over time. Now, this data, we can use this. Now, this data is the basis for our actual observation of the change in temperature. So, if we compare this data to the numerical models that we have, then we can identify which was the cause of the global climatic change. Now, if we compared the natural variables that is possible to change the global temperature, we can see that the model of the natural variables is not enough to explain the global climatic change in global temperature. As you can see from here, the red line represents the observed temperature, and the gray lines represent the model. Now, why is the model thicker? Now, that is because we need to put in some margins of error, right? In order to be because we can't be sure about our calculations. Now, as you can see from this, natural variables are not is not enough to explain the temperature that we are experiencing right now. Now, what about the greenhouse gases, the greenhouse gases that we humans emit? Well, see for yourself. As it turns out, the greenhouse gases that we can the radiative forcing that the greenhouse gases that we emit that contributes to the global change in temperature, as we can see from this data, the models, our calculated models or numerical models, patterns of change is similar to the patterns of change in the observed global temperature. As you can see, as the temperature change, the global, the calculated amount of CO2 in the atmosphere, or the amount of CO2 atmosphere, the amount of temperature change that CO2 induced during that time, you can see that there is a relation between the two. You know, there's a pattern of change. There's similarity between the two. Just look at this. For example, at the end of during the 1850s, we can see that the numerical models that we have for greenhouse gases somehow satisfies the global temperature change. Now, since natural variables and anthropogenic variables don't work alone, or don't work individually, because they are present in our globe, right? They are present everywhere. There is a need to combine the numerical models that we have for natural variables and anthropogenic variables. There is a need to combine them in order to see the global, in order to compare them to the global temperature change. And what we found out when we did that was this, right? This data was amazing because, our numerical models somehow satisfies the observed global temperature change, right? Look at this. The global CO2 emission and the natural variables that can affect global temperature work together in order to show us that the average temperature that we are experiencing right now. Now, with this model, we then identified the cause of the shift in global temperature, which leads us to humans, right? Now, our CO2 emissions are really the cause of the climate change or the temperature shift that we experience, right? Going back to that data, you can see that the temperature change that the CO2 emissions induced is barely enough. It is somehow enough to explain the global climatic change. Now, I just want to in order to refresh, I just want to refresh everything that we discussed. We first discussed the carbon cycle, which was essential in order to maintain the carbon amount present in the atmosphere and everywhere. We then discussed the amount of CO2 emissions that humans have, the CO2 emissions that humans have emitted since the Industrial Revolution. And then we also discussed the fact that greenhouse gases have the ability to store heat. Next, we then discussed the temperature change that we are experiencing right now and since the Industrial Revolution. Now, in this latest discussion, in this latest topic, we discussed how we knew that humans are the cause of the global climate change. Now, we know that the humans are the cause of the climate change because of the facts and observations that we have, right? the fact that greenhouse gases can absorb heat, and we observe that, and our observations and data tells us that the CO2 concentrations in the atmosphere has been increasing since the Industrial Revolution, which was not seen during the past in the Earth's history. Next, by using numerical models and comparing them to the data that we have, we then identified and proved that humans were really the cause of the global climatic change. Now, numerical models are, like I said, numerical models are our weapons in order to identify the global climatic shift. We first isolated the natural variables from the anthropogenic variables and created their own separate numerical models, and by comparing them to the observed actual global temperature, we then know which was the cause of the climatic shift. Comparison. Now, I just want to bring this photo back. Now, given all of the lesson, or given all of the topics that we talk about in this time, I think you now have the capacity to decide, to decide for yourself whether climate change is really a serious problem. Alright? It's up to you to decide whether climate change is really a problem or it's just nothing. Also, take into account that we humans are not the only living creatures or living creatures here in the planet Earth, right? There are also other organisms and animals that we should take into account if we were to judge whether climate change is whether climate change is a serious problem. Now, as we recent advances in I just want to share with you that in the IPCC's latest assessment report, we can expect an increase in global temperature by, I think, 1.5 degrees Celsius by 2040. We can expect a 1.5 degrees Celsius increase. Now, maybe to us humans, that 1.5 degrees Celsius increase is, that can't affect us, right? The 1.5 degrees Celsius, that can't affect us. But we have to take into account that we are not only the humans. We are not only the living organisms that exist in this planet. We have also to take into account whether other living organisms can survive the increase in temperature by 2040. Excuse me. Now, we will then discuss. I will share with you some of the latest technologies that we have in order to combat climate change. Now, as we all know, we are aware of the solar energy development that most of the companies are doing. Most large, big companies are doing. Elon Musk and Bill Gates. They are creating They are creating advances in the renewable energy route. Now, renewable energy sources are one of the technologies that we are using right now. Now, there is also carbon capture and storage. Now, as far as I know, carbon capture and storage is like to be honest, I'm not really sure what carbon capture and storage is, but they say that it is also a substitute to the it can reduce the atmospheric concentration of carbon dioxide in the atmosphere. I think that's what it is. And then we also have a hydrogen as energy source. Now, as you can see from all of this list that we have, all of these technologies that are being developed, all of these advances are with regards to energy sources, right? Just like we said, the um the um the organic or the land energy sources that we have right now, or the dirty energy sources that we have right now, is the foundation of today's today's age, right? Fuel from coal, carbon energy sources are the foundation of today's age. So if we really want to it is the foundation, so we have to find a way to replace the carbon energy as a source. We have to replace carbon. All right, so that is why most of the advances in technology in order to combat climate change is with regards to energy sources, because we should pull everything out from its roots, right? Which is the source of energy. Yeah. So, what can a simple individual do? Well, I think that a simple individual what an individual can do is to just if they are knowledgeable about the issue of climate change, why not share it to everyone around you? Spread awareness. I mean, it's a good act to share knowledge with regards to the problem that we are facing right now, because I really think that sharing information and spreading awareness with regards to this topic is a very big thing for an individual to do, right? It is not just a simple task, right? Even though you think that it may seem small, it is really a big task. I mean, it can have a massive effect, right, to the way they think and they view the science of climate change. And also, I think that creating sustainable projects with regards to climate change, creating something like that, as a student, I think that that's a helpful way to help the science community and the earth as a whole. All right, so I think that's it. Yeah, maybe you're thinking that humans are a simple individual can't really help in developing technologies. Well, that's true. Most of us can't help in developing technologies, but what we can do is spread awareness and share knowledge and information out there. We are all on social media. Share everything about the climate, about the issue of climate change and the science of it. It's amazing. It's an amazing thing to share knowledge. Now, I'll bring you back this photo. Now, just like I said, climate change is not about us. We have to take into account almost every organisms and living things on Earth. We have to take into account whether they can handle animals like them, whether they can handle the shift in climate. All right? Maybe we humans can, but can the animals and the plants withstand the increase in temperature? I mean, it will take them time in order to adapt to their new environment. So let's not be selfish and only think about ourselves. We also have to think about every every living creatures on Earth when we talk about climate change. Alright? I think that most of us humans think that climate change is not hard. Climate change is not a serious problem because we can stand it. We can withstand it. We can withstand the change in temperature. Yeah, we can withstand it. But just like I said, we have to also take into account every human beings in the planet Earth. And you will see, and when you do that, you will see why climate change is such a serious problem. Now I leave you with this. We are the problem, but we are also the solution. I believe that we can solve the problem of climate change, no matter how slow it may seem. The actions that we take will lead us somewhere, and I know that I have faith that we can solve the problem of climate change, and yeah, we can make the world a better place for all of us. And yeah, so that's it. So thank you for finishing the lecture. I commend you for finishing the lecture with regards to climate change. Now, just like I said earlier, just like I said earlier, I'm just a person, a student, sharing the lessons that he have learned from his research on climate change, and I just want to share this knowledge with you. Thank you for finishing the video, and also I will leave down below. I will post the link to my research paper. To my research paper with regards to climate change. Mainly it is a report. It is a report, and if you like, you can read it. It's free. No, I don't charge anything for it. I just want to share that climate change. I just want to share knowledge with regards to climate change, and I hope that I gave you an understanding with regards to this topic. So thank you, and I'll see you on the next one.